Hello everyone, Mr. Bowman here. In section 8.3, we are going to talk about constructing confidence intervals to estimate a population mean. In section 8.1, we talked about confidence intervals in general. In section 8.2, we talked about confidence intervals to estimate a population proportion. And now we're going to talk about confidence intervals to estimate a population mean. So it's very similar to any confidence interval, except that we have to check the conditions in a slightly different way for normality. Other than that, everything is the same. So what we're going to do right now, and this is somewhat contrived, is we are going to assume we know the population standard deviation. And that's contrived because if you knew the population standard deviation, you use the population mean to calculate the population standard deviation. And so if you knew the population standard deviation, you would therefore know the population mean. The reason that we do that is because it's simpler to talk about the process of constructing the confidence interval, assuming we know the population standard deviation. But in the next activity, we'll talk about how we address the fact that we don't really know the population standard deviation. So if we want to construct a confidence interval to estimate a population mean, we need to have a simple random sample. So there's our random condition. We need to have independence within the sample. So the subjects within the sample are independent of each other. And to do that, we need a sample size that is less than or equal to 10% of the population. And then we also have to have normality of the sampling distribution, which we verify by looking at the sample size or knowing ahead of time that the population is approximately normal. So here is the general formula for any confidence interval. You take a statistic and you go up and down from that statistic a certain number of standard deviations. That's your critical value based on the level of confidence you want. And you multiply that times the standard deviation. So that part highlighted in blue there is considered our margin of error, and that part in yellow is considered our point estimate. So what does the formula look like for proportions? Well, there's your sample proportion, that's your point estimate, and your critical value is based on a normal distribution and the standard deviation of the statistic. So when you multiply those two together, you get your margin of error. In a similar way, the same idea applies for means. We have our point estimate, which is our sample mean, and we have our critical value, which is based on our level of confidence, and then we have the standard deviation of our sampling distribution. So I would like to go back to our SAT example from earlier in the chapter and construct a confidence interval for that. So we're going to estimate the average SAT score for all 350,000 high school seniors in California. Remember our sample mean, 461. We had a random sample of size 500. Using the fact, we'll call it the assumption that the population standard deviation is 100 and our sample size is 500. For this sampling distribution, we're going to construct and interpret the confidence interval. Assume that all of the conditions have been met. So we have a random sample, our sample size is less than 10% of the population, and we meet the normality condition. Based on the given information, we don't really have to assume that, but sometimes you're given problems like that where it says assume the conditions are met, and you don't have to therefore check all of the conditions and write down how you check them. So we're going to do an 80% confidence interval here. And so the first thing I want to do is I want to illustrate to you the easiest way to find the critical value. Now, as you know, if you are doing a 95% confidence interval, you basically would have to go out approximately 2 standard deviations, and you could think of this middle 95% of the distribution here to help you figure out what your critical values are. And the critical values, or critical value, is basically telling you how many standard deviations in each direction you need to go to be that level, to have that level of confidence. So the way I would find the critical value for a 95% level of confidence, if I didn't have it memorized already, is I would use the inverse norm function. So z critical value would be equal to inverse norm of, and remember what inverse norm does. You are required to put the percentile in, and it will return to you the corresponding value. So ignoring the negative here, the percentile corresponding to the critical value on the right there would be 0.975. And the reason for that is because you have the middle 95%, but then you also have the upper and the lower 2.5%. So when I add those together, I am telling the calculator that the percentile is 0.975, which means I would get a critical value of 1.96. So we're going to do the same thing, except we're going to do an 80% confidence interval. And so imagine the middle 80% of the distribution, remaining 10% on each side. And so our critical value is going to be the following. Critical value is equal to inverse norm of 0.90. And if you do that on your calculator, the way you do that on your calculator is the following. You hit second and the distribution, and you go to inverse norm, and you tell it the area, so 0.90. Leave the mean and the standard deviation at 0 and 1 respectively, because that's for z-scores. We get a critical value of 1.28. So we need to go 1.28 standard deviations in each direction for our 90% confidence interval. So our 80% confidence interval. Our confidence interval is going to be the following. It's going to be 461 plus or minus 1.28 times our standard deviation of the sampling distribution, which is 100 over the square root of 500. And that is our 80% confidence interval. Now, what I want to show you next is how to have your calculator do this for you, because this is the minimum amount of work that you have to show. You don't have to show any of this stuff over here on the left-hand side. The only reason I put those calculator commands down there is to show you how to do that. But what I would highly recommend at this point is that you switch to the calculator and you let the calculator find this confidence interval for you instead of punching this all in on your home screen. So here's how you go about doing that. So if you go over here and you hit you hit stat, and you go over to tests, there's a whole bunch of tests here, and you're going to have to figure out these as we go along and remember which ones are which. So z-test, t-test, 2 sample z-test, 2 sample t-test, 1 prop z-test. There's a whole bunch of them. But what we have is a confidence interval. And what we're doing here is we are doing a z-interval. Why is it a z-interval? Well, we're going to change how we do this after we deal with the fact that we don't really know the population standard deviation. But for now, if you know the population standard deviation, when you are constructing a confidence interval for a mean, you are going to use a z-interval. So if you select that z-interval, you have 2 options here. Data, which would be you entered the sample data into lists, and you're going to use that, or stats. So we're going to select stats. we're going to go to our population standard deviation, which you'll remember we assumed was 100. That also is an indicator that you're using the right thing because it's asking for a population standard deviation there and not a sample standard deviation. Our sample mean, 461, and our sample size, 500. The confidence level as a decimal, 0.80, and then we're going to calculate. And what this does is gives us the lower and the upper confidence limit. So our 80% confidence interval goes from 455.27 to 466.73. 455.27, comma, 466.73. And then remember how we would interpret that. We would interpret that in the following manner. We are 80% confident that the population mean SAT score for all 350,000 California high school seniors lies somewhere in the interval from 455.27 to 466.73. And if we were interpreting the confidence level, 80% confidence level means that if we were to construct all possible 80% confidence intervals from this sampling distribution that consists of all samples of size 500, 80% of them would contain the true population mean. So I'm going to skip ahead now past this, how to use your graphing calculator for this, because we already talked about that. I'm going to go down here to what our book calls the four-step process. The four-step process for a confidence interval, they say state, identify the population of interest and the parameter you want to draw a conclusion about, include the appropriate inference procedure in the context of the problem. To be honest with you, most of the time I think through this and I don't actually write this down, but for you to illustrate it for you, I'm going to do that. Plan, verify the conditions for the procedure are met. So far, was it a simple random sample? Is the sample size small enough to meet the 10% condition? Do we meet the normality condition for the sampling distribution? Do actually carry out the calculation. Show your work. Don't bother writing down calculator commands. They will be ignored as if they're not even there. Show what you're plugging into each of the values, and then use your calculator's built-in z-interval function to calculate the confidence interval. And then conclude. Interpret the results based on the context of the problem. So the next example I want to work through is another confidence interval example, except in this case, what we have is we have a set of data of size 20. Okay, so if you read all this information here, it says, careful study has shown that when process is operating properly, the standard deviation of the tension reading is 43 millivolts. Notice that's population standard deviation, so we're going to use a z-interval. The table below shows the tension readings from an SRS of 20 screens from a single day's production. Your job is to construct a 90% confidence interval for the mean population tension mu. So we're going to go through this from start to finish following the four-step process, and we're going to use the calculator, but this time instead of using the stats option for the z-interval, we're going to use the data option. All right. So the first step in the four-step process, state, identify the population of interest and the parameter you want to draw a conclusion about. Define an appropriate population parameter during this step, if not given already in the problem. Also state the inference procedure you will be using. Again, I normally think through this. I don't actually write this down, and you are free to do the same, but make sure you don't skip it. So in this case, the population is all ABC high-resolution video terminals, and the parameter that we're interested in estimating is the population mean. Plan, verify that the conditions for this procedure are met. So let's go back here and read this paragraph carefully and make sure we met those conditions. It says the company table below shows the tension readings from a simple random sample of 20 screens from a single day's production. All right, so we know that it's a simple random sample. It's stated. So when you're checking the conditions, do not write the condition name down and simply put a check next to it. If you do that, it will get marked wrong. We're not going to assume that, nor are the graders of the AP exam going to assume that you know the condition has been met simply by putting a check next to it. So in this case, a simple random sample was stated. Have we met the condition for independence? Well, our sample size is 20, and if this company is in business to produce high-resolution video terminals, I would assume that they make more than 200 high-resolution video terminals. So I believe that 20 is easily less than 10% of all the monitors. And now we need to check the normality condition. Well, it was not stated anywhere in the problem that the population is normally distributed. It actually did not say anything about the shape of the population, and we have a sample size that's less than 20. So we don't know if our sampling distribution is approximately normal. So we have a way of dealing with that. And listen carefully because this comes up quite often. So since we're not sure if the population distribution is approximately normal, the next best thing we can do to test that theory is to take a random sample of the population. And if the random sample from the population appears to be approximately normal, then we can assume that the population is approximately normal, and therefore we've met the normality condition for our sampling distribution. Well, so how do you check normality for a sample of size 20? You could do things like make a dot plot, you could make a histogram, you could make a stem and leaf display, you could make a box plot. None of those are very good, particularly for small samples, at determining whether or not the sample is approximately normal or not. The best option is to use a normal probability plot. And we did that before first semester, and we're going to talk about that again. So here's how you make a normal probability plot using your calculator. You enter the data into your calculator, which I have done here in list number 3. Be careful when you're entering data. Take your time. Make sure that you have the right number of numbers in there and so on. And then after you've done all that, you hit second and the stat plot button, or second and the y equal button. You select one of the plots and turn it on. And you scroll down to the type of plot, and the normal probability plot is the very last one. If you are going to use a normal probability plot, you have to put all the data in one list. So I happen to have the data in list 3, so second and the number 3. The data axis could be the x or the y axis. I usually put it on the x axis. Doesn't matter. The mark, I would use one of the bigger ones, not the small dot, because it'll be hard to see the small dot. And then hit zoom 9. So when you hit zoom 9, and I've got some other stuff in there I need to get rid of, so I will clear that stuff out and then graph it again. If you recall, when the normal probability plot is linear, that indicates that the sample came from an approximately normal population. So it's fairly linear here. We've got a little bit of a departure from normality right there, or for linearity in the middle. But since we have a sample size that is relatively large, our departures from normality or from linearity and therefore normality are not a big deal. So we're going to assume that we met that condition. So now that we've actually checked that, we go ahead and we calculate the 95% confidence interval. I'm sorry, it's not a 95% confidence interval. It is a 90% confidence interval. So how do we actually do that with data? So here's the way to do this with data. We've got the data in our calculator in list 3. So I'm going to hit the stat button. I'm going to go over to tests, and I am going to select Z interval number 7, and I'm going to switch over to data, and I'm going to tell the calculator what I am assuming the population standard deviation is. And in this case, we were assuming that the population standard deviation is 43. I'm going to tell the calculator what list the data is in. I happen to have it in list 3. How often what's the frequency of each value in that list? I'm going to count each value once. And then the confidence level, and we're doing a 90% confidence level, and then we're going to calculate this. Okay, so a little word here about showing your work. The calculator shows you the final confidence interval, which is fine, and you should write that down. But if that's all you write down, then you will get it wrong. So be careful about showing your work. So I don't know if you noticed this or not, but if you compare what I have as a solution in my notes, my confidence interval in my notes goes from approximately 290 to 322, but in my calculator, I got a different answer. And I think this is a good example of how easy it is to make a mistake when you're entering data. So to point out my mistake, I go back to the data here, and I went through this, and I found that my last entry was wrong, and it should have been 336. So I'm going to go ahead and change that and hit enter, and then we're going to go ahead and do this calculation all over again. So stat tests number 7, all the information is there already, and we're going to calculate this. And there we go. There's the correct confidence interval. And I only know that because I've already done this problem. But in terms of showing your work, go ahead and write down the confidence interval, but then use the sample mean 305.9, which is calculated by the calculator for you, the sample size, and the assumed population standard deviation to show your work. So 305.9, critical value, assumed population standard deviation over the square root of the sample size. You need to show your work, and then go ahead and write down the confidence interval that you got. If you write down a confidence interval without supporting work, you will not receive credit for it. And then the last thing we want to do is we want to interpret the confidence interval in context. So our interpretation is going to go something like this. We are 90% confident that the population mean, or the mean tension of the population, lies in the interval from 290.08 to 321.72 millivolts. And the calculator information here just talks about how to do that on the calculator, which we talked about. So we're going to move on to talking about one last thing in this video, and that is how to select the necessary sample size if you are interested in a particular margin of error. So the first thing we're going to do is we're going to start out with the confidence interval formula for a population mean. So x bar plus or minus the critical value times sigma over the square root of n. And this portion right here is the margin of error. And very often you are expected to have a certain margin of error, 5%, 3%, 2%, whatever the case may be. And you also want that to be with a certain level of confidence. So what that leaves for you to do is to determine the sample size. So let's say we want to go back to the example we just did, and we want to ensure that the margin of error is less than 5 millivolts at the 90% level of confidence. So the way we would do that is the following. We would say the margin of error, I call it the MOE, the margin of error is equal to 5, because that's what the problem says. We'll set it equal to 5. That is the critical value, which, by the way, the critical value we earlier calculated for a 90% confidence interval, and we calculated that to be 1.64 times the assumed population standard deviation, 43, over the square root of the sample size. And now, through the black magic of algebra, we can solve that for n. And when you solve that for n, you always need to round up, because if you round down, then n is going to be too small to meet your conditions for the margin of error that you want. So how do I go about solving this algebraically? Here's what I do. I would divide both sides by 1.64, so get 5 divided by 1.64 is equal to 43 over the square root of n. I would then square both sides, and when you square the right-hand side, you get 43 squared over n. So at this point, you have 5 over 1.64 quantity squared is equal to 43 squared over n. I typically just take the reciprocal of both sides, so then you have 1.64 over 5 squared is equal to n over 43 squared. And then I would multiply both sides by 43 squared. Now, you can go about solving this however you like, but make sure you show your work and make sure you check your answer. So when you do this, you get an answer of approximately 198.9. So to round that up to 199, and that will give you your correct answer. And you can go back and verify that by plugging that into our original equation for n and making sure that the right-hand side is going to be slightly less than 5. Again, always round up. Even if the number that you got doesn't technically round up, for example, if we had gotten 198.1, you would still round up to the next highest number. All right, what sample size is needed to cut the margin of error in half? Well, you can verify this algebraically, or you could kind of think through it. So to verify it algebraically, you would basically say, oh, I'm going to make the margin of error 2.5, same critical value, same assumed population standard deviation, and solve for n. And what you would find is that the sample size would have to be 4 times larger. So to cut the margin of error in half, our sample size would have to be 4 times larger, or 4 times 199 in this case, and that would turn out to be 796, and you can verify that. So the last thing I would like you to do is I would like you to pause your video, do this check your understanding problem, and make sure that you know how to solve for the sample size correctly given a particular margin of error. All right, so here is the necessary work. If you wanted to be 98% confident, you'd find the critical value using inverse norm of 0.99. You do not need to show that. That's just an illustration so that you know how to do it. Set up your equation. The margin of error had to be 0.0001, critical value 2.33 to be 98% confident, assumed population standard deviation of 0.0002 over the square root of n, solve for n, and you get 21.7, and you round up to 22. So that is the first lesson in constructing confidence intervals and calculating necessary sample sizes to estimate population means. In the next video, we're going to talk about how to deal with the issue of not knowing the population standard deviation.